Right, so I'm going to give a preview of the session called Automated Verification. The session is also at 13:20 in the afternoon today. My name is Viktor Kunčak, and the session I'm going to preview consists of 4 papers, one of which is a distinguished paper. Turns out, despite the diversity of these techniques, there's a lot in common, and I'll try to set some context for that. So the idea in this field is that we want to design algorithms that exactly solve a specified class of verification problems. So sometimes this is related to algorithmic verification for this reason. All people in industry like to talk about push button verification, where we don't need to provide additional hints. And you can use that as a subroutine of a more manual task. For example, if you're a user of a proof assistant, you can think of this as a science of building tactics and understanding when they work. Right? So SMT solvers, model checkers, and so on would also all belong to automated verification. And so we would like to have soundness and completeness guarantees. So that the answers are always correct, whether we report a verification that property holds or that there's a counterexample. And often we study properties of these algorithms, such as worst case complexity. And sometimes you may find some pretty high complexity classes here, but nonetheless people implement these algorithms and they evaluate them on examples that we encounter in practice. And what is key, when some of these properties do not hold, often what you do is go back and redefine your class of verification problems so that you have a characterization for which you can have then this property. So identifying interesting class of problems is an important part of this field. And so when we design this, we of course want to know when this characterization applies. We don't want characterization to be as complicated as running some expensive algorithm. And this might include some syntactic restrictions on programs, program states, length of executions, number of sessions in a protocol, a number of processes, and so on. Okay, so let me take a very simple example that should be familiar to all of us. So consider a program, and suppose that we can represent it by a finite state machine M, and suppose that we have a set of permissible program traces, and we can represent it maybe by a regular expression as a more declarative representation. And suppose that could be, for example, we mentioned file. So if you open a file, then you read and write any number of times, and then you close the file. So that would be specifying the desired properties of some traces given by these actions: open, read, write, and close. And so our question is, do all traces of this finite state machine actually belong to this regular expression R? And you can probably imagine the algorithm to do that. You take this regular expression, convert it to a deterministic finite state machine. Let's denote it MR. Then you complement this, then you get a complement. Then you take the product automaton, and that way you can check the intersection of the two languages. And this gives you the words that belong to this automaton, that are accepted by this automaton, give you counterexamples for your property. So if you find such counterexample, then this is actually a counterexample trace showing that there is execution that doesn't satisfy property. And otherwise, you actually can compute a regular invariant for every state of the automaton that says this is the reason why this property is satisfied. But so this is a very simple example, but it's an interesting starting point for all sorts of extensions. So I talked about finite traces or infinite automata, but you can look at infinite traces. And automata that have cycles, of course, can have also generate infinite traces where you just go through the loop infinitely many times. And these for finite state machines would be omega regular. But then you can generalize to push down automata, and there you can, for example, check procedure calls. And now this leads me to regular model checking, where you can talk about representing these states themselves and covering infinite state spaces. Now, model checking for finite state systems had a big boost with the adoption of binary decision diagrams in the works such as this one that were introduced by Bryant. And these can be viewed as finite state machines without cycles. Now, if you say that you have an infinite state space, for example, your spaces are strings, then you can say, well, let me permit cycles. So here there should be arrows going from up down. Then you can say, we can use finite state machines to represent regular sets, and we can discover invariants that are regular sets. Now, if you have a bound on the number of states of such machines, this gives you an algorithm that can verify a certain class of properties. For example, it is complete for this push-down automata for context-free systems that I mentioned. And now this leads me to the first paper, which is regular abstractions for array systems. Examples of array systems would be sorting algorithms that operate on arrays and distributed algorithms with processes such as symmetric processes, such as Dijkstra's self-stabilizing algorithm or Chang-Roberts ring-based election protocol. So in this work, there's an abstraction from programs that manipulate these arrays into programs that work on strings. And this abstraction uses actually quantified invariance, which is a very nice concept that generalizes abstraction with some fixed quantifier-free predicates, and it was used as far back as in the work of Lahiri and Bryant. And then the result of this over-approximation is a system that is still infinite state, but that you can then model check using regular model checking techniques. And one of the techniques that's used here is L-star learning algorithm that discovers finite state machines from examples. In this case, these would be counterexamples. And so this is one of the techniques that is used here. And this abstraction is designed in such a way that actually can also preserve liveness properties. So this work actually does handle classes of liveness properties. And there are many more details. I encourage you to look at the paper and attend the talk. And I'm going to now move to a slightly different topic, which is verification of first-order logic properties, which sounds like a fairly independent deductive problem. But in fact, it is motivated by verification of distributed systems as well. And well, first-order logic is sufficient to axiomatize all the knowledge of mathematics. And one example of that is actually a Mizar system that used set theory in schematic first-order logic that axiomatize this. And we also have work on using proof assistance based on set theory, as well as you can find this in other proof assistance. And now, given that first-order logic is very general, it is also important to know that it is of great practical interest, and in particular, it's been used in verification of distributed protocols. And we know for a long time that for first-order logic, two problems are semi-decidable, which is a given first-order logic formula valid, which is equivalent to it being provable. First-order logic is very nice in that respect, unlike some other ones. And the other problem is, given a first-order logic formula, does it have a finite counterexample, an example where the formula is false? And so we could enumerate proofs to answer the first question. We can enumerate increasingly large counterexamples, finite ones that answer the second question. But unfortunately, there's a third case, and that's why the problem is not decidable, only semi-decidable. And these missing cases are all formulas that are not valid, but their counterexamples are infinite. And so to another piece, and this is what this second paper addresses, the infinite needle in finite haystack. And this is a distinguished paper as well. And here the idea is that we are searching for representations of these infinite models. So here's an example representation. It is, as you can see, a finite graph, but you can define its expansion, which is an infinite structure in this case. So it's motivated by a distributed protocol, abstraction of Paxos. And here what we allow is certain relation that keeps repeating, in this case, a previous link. And this is related also for a class called effectively propositional logic or first-order logic, and this generalizes all these results. How much time? Yeah. All right. Okay. So the liveness properties permit all the works in this session, and one class of liveness properties is shown here. Is verification of liveness for distributed protocols using ranking functions, which actually was shown to apply to a number of protocols of interest. So that's this one. For example, Paxos variant was shown in this remote talk that will be presented. And finally, Dole-Viao model of cryptographic protocols is one piece of background that is essential for a final talk that gives a very nice classification of decidable and undecidable fragments and extends what was possible before. So I hope you attend this interesting and very deep session. Thank you.